Hello students, welcome back. Today we're going to be learning about matrices and Gauss-Jordan elimination. So previous few lessons we were dealing with system of equations, system of two equations, three equations, substitution, elimination, Gauss elimination. So now let's introduce matrices. So help us to actually perform system of equations much faster. So let's take a look at definition of matrix. So if m and n are positive integers, then an m by n, read it as m by n, matrix is a rectangular array of numbers, right? So we have columns up to n columns and m up to n rows. That's why it's m by n, rows by columns, in which each entry, a sub ij of the matrix, is a number. An m by n matrix has m rows and n columns. Okay? So let's go ahead and take a look at it immediately. So if we have a system of equations, so we can have x minus 4y plus 3z is equal to 5, negative x plus 3y minus z to negative 2x minus 4z is equal to 6. Right, this is system of equations. So we can actually rewrite it as an augmented matrix. So an augmented matrix will also include the right-hand side of the system of linear equations. So let's take a look at it. So we can have, well, first, augmented matrix. So it will look like the following. So we're going to have, we always have to make sure that we arrange the coefficients in the order of x, 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 y, 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 right? Because if we're going to be doing a matrix, we're going to be forming it the same way. So the first column is all of the x's, the second column is all of the y's, the third column is all of the z's, and the last essentially going to be column there, which is going to be augmented column. So let's take a look at it. So we're going to have 1, negative 4, 3 as the first row matrix, then negative 1, 3, negative 1 as the second row, and then we have 2, then we do not have a y, we put 0, then negative 4, right? So this is the coefficient matrix. Then we're going to put a line, and across the line we're going to put the values of the right hand side. So it's going to be 5, negative 3, 6, right? So this is augmented matrix. So now we do not have to worry about where x and y and z add. All we have to worry about is the rows of numbers. So we can perform the same operations as we did in the previous lesson. So we can have a row 1, row 2, and row 3, or the equation 1, equation 2, equation 3, because we keep in mind that the first column is x, the second column is y, the third column is z, and the fourth column are the right-hand side across the equal sign. Okay, but here we can perform all of the algebraic operations we want and find the solutions. So we can do the row echelon form, where we have just ones across the main diagonal, right? Because if we have the main diagonal here and we have 1, 1, 1, that's going to be essentially z, y, x. Right, so this is the most important part. The rest should be 0, right? This should be 0, this should be 0, this should be 0. That would be a row echelon. Okay, and of course we can also have the coefficient matrix. So the coefficient matrix, we will have the following. So it's just going to be the coefficients. So it's going to be 1, negative 4, 3, negative 1, 3, negative 1, and then 2, 0, negative 4. Right? Why do we need the coefficient matrix? Later on, we're going to learn about an inverse, because sometimes we don't even have to worry too much about solving it correctly. We might be able to find an inverse and do it through the inverse, and sometimes it's going to be faster than just solving correctly. So, but sometimes some equations might not have an inverse, that they are not going to have a solution. So, okay. So once again, let's recall what can we do, what kind of operations we can do, right? So of course, we can interchange the rows, right? We can interchange the rows. We can multiply the row by non-zero constant. So in this case, c constant times r sub a, where a is the number of row we're working with. And then we can add multiple of a row to another row, right? We can add multiple rows and multiple rows as we desire, as long as we follow the rules of algebra and do not violate by adding an extra row, subtracting an extra row or column, right? As long as that will be okay. So, all right. So we can practice some of it with the Gauss elimination system, right? But now we're going to be doing it in terms of the matrix. So we can recall a problem from the last lesson. We had x minus, so example 2. We're going to have x minus 2y 3z is equal. Okay, and then we're going to have negative x plus 3y is equal to negative 4. And we got 2x minus 5y plus 5z is equal to 7. Okay, and let's go ahead and actually rewrite it in the matrix form. So in the matrix form, we're going to have 1, 2, 3, and negative 1, 3, 0, 2, negative 5, 5, right? And we're going to do it as an augmented matrix. So here, we're going to have 9, negative 4, 17. Okay, and now, once again, doing same process, we have row 1, row 2, row 3. So the first step, what I'm going to do is I'm going to say add row 1 and 2, change row 2. So R1 plus R2, change row 2. Okay, so in this case, you don't always have to write down what operations you're as with it. So as you do more practice, it becomes intuitive and you can do it quite quick in your head. So, but here, it's always good to practice. So we're going to have our first row remains the same, 1, negative 2, 3. Our second row becomes 0, 1, 3. And then here it's important, we had a 9 here, it became a 5. Right, so we have to reflect that in this column as well. And then the last row is 2, negative 5, and 5. Okay, now the next step. Next step is going to be, well, we're going to multiply the first row by negative 2. So we're going to have negative 2 times 1. So this is our, again, row 1, row 2, 3. And we're going to add it to row 3 and change row 3. Okay. So we will have, so the first row is good because it has 1 right here. So we are okay. So 1, negative 2, 3, 0, 1, 3. And so what happens to the third row? It becomes 0, negative 1, 1. And the right column is 9, 5, and became 1. Perfect. Now, what we got to do is, next step is going to be adding row 2 to row 3. So row 2 plus row 3 and changing row 3. Great. So we're going to end up having 1, negative 2, 3, 0, 3, and then the third row becomes 0, 0. Running the augmented part, and we're going to 9, 5, 4. Then we're going to go ahead and multiply third row by the third row by 1/2, right? Essentially divided by 2, and we will have the following. So 1/2 times row 3 becomes row 3. So that's a new row 3. Okay, and we will have the following. So our row echelon form will be 1, negative 2, 3, 0, 1, 3, 0, 0, 1. It's going to be 9, 5, 2. Right, and now we can rewrite it again as an equation. Keep in mind, we had this is x, this is y, e, and this was the equal to the right-hand side. So we have x minus 2y plus 3z is equal to 9. Y plus 3z is equal to 5. And z 2. Right, this is the same thing. Those two things are identical. Okay, but the left side is more convenient and faster to use rather than write every variable over and over and over again. Okay, so of course we can have a reduced row echelon, right? So reduced row echelon form, that's essentially the Gauss-Jordan elimination. The reduced row echelon form is essentially when we only have the diagonals of ones and the rest is 0. So what can we do here is, well, we still have row 1, row 2, row 3. So we're going to take negative 3 times row 3 plus row 2, change row 2. So what are we going to have here? We're going to have 0, 0, 1, 2. Then it becomes 0, 0, 1, 0, right? And then here, it will become negative 1. Okay, and what else we can do? We can also do, well, now we can take row 2 here. So if we do a row 2, or actually we can do both. We could first do row 3 times -3, row 3 plus row 1, change row 1. Then we can, okay, so let's do that. So it's going to be 1, -2, 0. And then here, we will multiply by -3, so it's going to be 3. Okay, now that's going to be our new row 1, 3. So now we got to get rid of that -2. So -2, we're going to have row, so 2 times row 2 plus row 1, change row 1. So our final answer is 1, 0, 0, 1, 0, 1, 0, -1, 0, 0, 1, 2. Right, this is a reduced row echelon form, and what does it actually tell us? It tells us that x is equal to 1, y is equal to -1, and z is equal to 2. Right, so that gives us full solution. We don't have to rewrite anything. So depends what's comfortable. So sometimes it's straightforward row to reduced row echelon form, sometimes it's the row echelon form, and we can just solve it. So, okay, let's take a look and let's summarize how can we get the reduced row echelon form and echelon form in general. So a matrix in a row echelon form has the following properties. So any rows consisting entirely of zeros occur at the bottom of the matrix, right? So every time, if we have, for example, a full row of zeros, we move it, if it can appear anywhere in the matrix, we have to make sure that we move it all the way down at the bottom, right? Because we can flip them and we can move them around as we wish. Okay. 2, for each row that does not consist entirely of zeros, the first non-zero entry is 1, called a leading one. For 2 successive non-zero rows, the leading one is in the higher row is farther to the left than the leading one in the lower row. So as we go, as the stairs, right, we have to always form a triangle of zeros, right? So 1 here, 1 here. We should always arrange them like that. Even if we end up with different ones, because we can end up with different ones, we have to arrange it like that. So a matrix in a row echelon form is in a reduced row echelon form when every column that has leading one has a 0 in every position above and below. So this one, 1, 0 everywhere, the right to the left. 1, 0 everywhere, left, right, top, bottom. 1, 0 everywhere, all the way to the left are 0. Okay, so this part is the most important part. This is the one we are talking about, the reduced row echelon form, only about the coefficient matrix, not the equal sign to the right. Okay, perfect. So, and of course, how can we do the Gaussian elimination? So the Gaussian elimination is going to be done through the following. So we're writing down the augmented matrix of the system of linear equations as we did in the example. Then we're using their elementary row operations, as we practice here, to rewrite the augmented matrix in a row echelon form. And then we can write the system of linear equations corresponding to that matrix in row echelon form, or we can also do the reduced row echelon form, and then we're going to get the answer straightforward. Right? Perfect. So let's see. Let's actually go ahead and take a look at one more equation here. So, because sometimes the row echelon form doesn't only apply to the square matrices, we can also have a non-square matrix. So let's take a look at this one. So we have 2x plus 4y minus 2z is equal to 0. 3x plus 5y is equal to 0. Right, so what matrix form are we going to have? Well, it's going to be 2 rows, 3 column matrix. So we're going to have 2, 4, -2. Then 3, 5, 0. Then the line, and it's going to be, actually, let me put this one. This one's not going to be 0. This one's going to be 1 here. Do it like that. It's going to be 0 and 1. All right. So we have the matrix form. So now let's start operations. So let's go ahead and say, well, we're going to multiply by 1/2 row 1 and change row 1. So we're going to have 1, 2, -1, 3, 5, 0. 0, 1, right? So that was pretty easy. Now, the next step, let's go ahead and multiply the row 1 by -3 plus row 2, and then change row 2. Okay, so we're going to end up with, so the first row is 1, 2, -1. The second row will become 0, -1, 3, 1. Okay, then, well, let's go ahead and multiply row 2 by -1 and change row 2. So we're going to have 1, 2, -1, 0, 1, -3, 0, -1. Okay, and now let's go ahead and have -2, row 2 plus row 1, change row 1. Have 1, 0, 5. We'll have 2, and here we have 0, 1, 3, -1. Okay, so that's it, right? We cannot simplify it any further anymore because we're just going to be circle here. So let's write it down as an equation. So we're going to have x plus 5z equal to 2, and y minus 3z equal to. So this is a system of equations that we cannot solve because we have 2 equations and 3 unknowns, but we're going to say that z is our parameter. So we're going to say, well, let z our parameter. Then we're going to have that y is equal to 3 times t minus 1. X is going to be equal to -5t2. Okay, and that's going to be our solution. So t, so we have infinitely many solutions, right? As we choose t, we can have more and more solutions. So, but here we would write it down as following. So x would be -5t plus 2, comma, 3t minus 1, comma, right? So that would be our solution going to the system. Okay, and oftentimes the matrices are much more efficient than any of the algebraic manipulations that we can do, because it's convenient. So, okay, let's take a look at some of the properties of the matrices in general, because matrices is a very important part in mathematics. So the properties of matrices is as following. So we can denote it the following way. So a matrix can be denoted by an uppercase letter, such as A, B, or C. A matrix can be denoted by a representative element enclosed in a bracket, like this, right? I and J means the row and column. And the matrix can be denoted by a rectangular array of numbers, such as we did in the matrix system of equations. Okay, so inequality of matrix. So essentially, in order for matrix, I'm going to do a square matrix, A, B, C, be equal to a matrix E, E, F, G, H. That will only happen if and only if A is equal to E, B is equal to F, C is equal to G, and E is equal to H. Right? That's when it happens. Right? So this is very, very important. Okay, then how, for example, we would add matrices? So we would add it the same way as we add equations, right? Component by component. So, or coefficient by coefficient. But essentially, if we have two matrices, A and B, and we have a dimension of a matrix m by n, then their sum is m by n, right? Which would be A plus B. So we're adding each of the component, right? So an example, I'm going to do also two. We have 1, 2, 3, 4, plus 2, 1, 5, 7. So our final matrix is going to be 2 by 2. This is by 2. This is 2 by 2. So we're going to have 1 plus 2, 1, 3 plus 5, 4 plus 7. So our final matrix is 3, 3, 8, 11. Okay? So we're directly adding component by component. And if we would have a 3 by 3, then we would do 3 by 3. But we cannot add. We cannot add matrix that would be at different dimensions. It would not be doable. So, for example, if we add, so if we had A to B, 2, 1, 0, 4, 0, -1, 3, -2, 2, and we decided to add it to a matrix B, and B would be something 0, 1, and -1, 3, 2, 4, right? We cannot add it. This one's 3 by 3. This one's 3 by 2. So A plus B doesn't exist. So can't add it. And add it. So there's nothing. We cannot add it together. Okay. Now, for scalar multiple of matrix, right, we can also do scalar multiple of matrix. So we can multiply the entire system of equations, and what would that be is essentially we're just multiplying everything by that coefficient. So if A is the matrix m by n and C is a scalar, then the scalar multiple of A, if we're multiplying it by A, we're going to have just each component of the matrix going to get multiplied by that C. So, and why is it important is because, well, if we want to subtract the matrix, so A minus B is going to be the same thing as A plus -1 times B. So we're going to put -1 to each of the entry of matrix B, and we would simply just subtract. I would simply just add the negative component of the matrix B, and that would be the number. So let's take a look. Let's say that A, so example 2.2. So let's say that A is equal to 2, 4, -3, 0, 1, 2, 1, 2, and B is equal to 2, 0, 0, 1, -4, 3, -1, 3, 2. Okay, so if I multiply, well, part A, so 3A is going to be equal to 6, 6, 12, -9, 0, 3. I forgot the negative. My notes. Okay, and then 2, 1, 1, 2. That's going to become 6, 3. Perfect. Pretty straightforward here. Now, if we decided to add A plus B, right, or actually do part B, so -1B, it would be -2, 0, 0, -1, or -3, 1, -2. Right, so now we can indeed add. So part C, let's go ahead and add 3A minus B. So that would be, we're just adding them together, right? Adding them together. So we're going to get 4, 6, 12, -10, 4, -6, 7, 0. Right, so we directly add. So 6 plus -4 is 4, 6 plus 0, that's 6, 12 plus 0, that's 12, -9 plus -10, 0 plus 4, -6, 6 plus 1 is 7, 3 plus -0, 6 plus, that's 4. Right? Now, so let's summarize what we have here. All of the properties of the matrix. So if we have, let A, B, and C m by n matrix, and let C and D be scalars, so then we have a commutative property, so A plus B is equal to B plus A. We can have associative property, so A plus B plus C can be the same thing as A plus B first, and plus C. Associative property of scalar multiple, scalar identity, distributive property, and distributive property for multiple coefficients. Okay, so that one should be pretty straightforward. So the only difficult part about the matrix sometimes may be matrix multiplication, right? And matrix multiplication is a tricky one. So we can multiply the two equations together, but that's going to be a distribution of components. So let's actually go ahead and define matrices. And so matrix multiplication. That one. I'm going to have a few examples. This is going to be the last topic. So matrix multiplication. So we have this. So if A is m by n matrix and B is B, n by p matrix, then the product of A by B is going to be m by p. Okay? Matrix given by the following: B, where Cij will be as following multiplication and addition. So, right, this one is quite tricky, and it's probably better if we take a look at the example. Right. So, let's say, so example 3.1. What I want to do is I want to say, okay, well, I have a matrix A, which is 3, 4, -2, 5, and matrix B, which is going to be 1, 0, 0, 1. So this is 2 by 2, this is 2 by 2. So the final matrix, if I multiply A times B, it's also going to be 2 by 2. But how are we actually going to do that? So 3, 4, -2, 5 times 1, 0, 0, 1. So how are we actually going to do that? Is as following. So the first one is going to be, we're going to multiply the row times the column, and that's going to be our first entry. Okay, so it's going to be 3 times 1 plus 4 times 0. Okay, that's our first entry. Then we're going to take the first row times the second column, and that's going to be our second entry right here. So that's going to be 3 times 0 plus 4 times 1. Right, so we're done with the first row of our new matrix. Now let's move on to the second row. So it's going to be second row times first column. So we're going to have -2 times 1 plus 5 times 0. Okay, and then we're going to have the second row times the second column. Okay, so we're going to have -2 times 0 plus 5 times 1. Right, and if we simplify, we're going to get 3, 4, -2, 5. All right, so that's going to be our AB. Okay, and so what we always have to watch out for is to make sure that when we multiply a matrix, we have the proper dimensions, right? But the operations like this are going to be the same. So 3 by 3 is going to be much longer because you are just doing each entry one by one, and you have 9 entries. You got to do it 9 times. But it's a good practice, so I would highly recommend you guys to practice. So, but let's go ahead and talk about the properties of multiplication. There's not that many properties for multiplication, but let A, B, and C be matrices, E, B, and scalar. So we do have an associative property, but it's very, very strict and important because we're not allowed to just jiggle around the matrices and flip them around, because if we flip them around, sometimes we might be able to be identified because we cannot do matrix multiplication due to rows and columns. So if A times B and C is going to be the same thing as AB times C, then we can distribute them from the left side, right? Left distribution law. We can also have a right distribution law. We cannot move, right? This is not going to be the same. This is crucial, right? This is not the same. So A plus B times C is not equal to C, A plus B. And in general, AB might not be equal to BA. So this is very, very crucial. This is not holding in matrices. We cannot assume that this is not always true. So we have to be very careful, because A times B is not equal to B times A. And we can just think about a matrix, different matrix. If we have a 3 by 2 and 2 by 3, or 3 by 2 and 2 by 4, right? We can still multiply them, but if we flip them, we're not going to be able to, because the dimensions not match. So the matching dimensions are very important. So definitely have to keep that in mind. And of course, the associative property for scalar multiplication, it doesn't really affect much, because we can move it to A, we can move it to B as we wish. And keep in mind one more thing. So when we were getting the reduced row echelon form, right? Reduced row echelon form, right? Reduced row echelon form, right? It looked like this, something like 1 0 0 0 1 0 0 0 1, right? So this is, we call an identity matrix. Identity matrix. And so identity matrix is formed as I of 3 by 3. Right? And so now the definition of the identity matrix is as following, right? We can have it in any dimensions as we wish. So the n by n matrix consists of all ones on the main diagonal and zeros everywhere else, is called an identity matrix of a dimension a by n, and is denoted the following way. So this matrix is square, and it only exists as a square matrix here. So when the dimension is known, we can denote it as I sub n, simply, without writing the 3 by 3 as I did. So this is the same thing as I3. Great, perfect. So next time we're going to have the inverse of the matrices, and we will do some of the actual application problems for matrices. Right, see you guys next time.